Okay, hello everyone. Welcome to our fortnightly appointment with these online meetings on evolved stars and systems. Today we have two talks regarding common envelope evolution and planets. And the first one is given by Felipe Lagos from the University of Valparaiso. Felipe, you can start.
Okay, thank you. So can you hear me right?
Yes.
Okay, so, hello everyone. Well, first of all, I would like to thank the organizers for the opportunity to present this research. In this work, we studied the case of WD1856b, which is a close giant planet candidate orbiting a white dwarf with a period of 1.4 days. To put a bit of context, this planet candidate was first detected by TESS, and then the transit was confirmed with the Carlos Sanchez telescope and the Gran Telescopio Canarias, and also Spitzer, indicating at the end that a planet or a very low mass brown dwarf is orbiting the white dwarf. This discovery was published in Nature last year on September by Vanderburg et al. In this cartoon from O'Connor et al. 2020, the white dwarf that we just call WD1856 is part of a hierarchical triple system in which the white dwarf is orbited by a M-dwarf binary located at more or less 1,500 AU. So, here we can see the planet candidate, and in this image, we can see the M-dwarf binary and the location of the white dwarf. In this table, we can see the main properties of the system, and the most important characteristic here are the mass of the white dwarf, the cooling age of the white dwarf, which is the time it takes for the white dwarf to cool down to its current temperature since its formation, and the orbital period of the planet. Furthermore, using the kinematics of the system, they conclude or derive that it is likely part of the thin disk of the galaxy, which marks an upper limit for its total age of 10 gigayears. They also derive an upper limit to the mass of the giant planet candidate of 14 Jupiter masses. So, now the big question about this planet candidate is how did it reach such a very close orbit? So in order to avoid its destruction or disruption during the metamorphosis of its hot star into a white dwarf, the planet must have been farther than at least 1-2 AU. So in this context, Vanderburg et al. Discussed several evolutionary scenarios that could migrate the planet inward, including dynamical instability in a planetary system when the host star evolved into a white dwarf, say Pell Kosailid oscillations produced by the M-dwarf binary, and also common envelope evolution. The first two scenarios produce changes in the planet eccentricity, which combined with the tidal dissipation in or close to the periastro reduce the planet's semi-major axis. In the last scenario, the common envelope scenario, once the host star evolves off the main sequence and overfill its Roche lobe, its envelope expands and engulfs the planet. Then the friction between the planet and the envelope transfer orbital energy to the envelope, reducing the final orbital separation and ejecting the envelope. So through embodied simulations, Vanderburg et al. Found that the most likely explanation for the short orbital period of the planet is the dynamical instability scenario, which is efficient for low planetary masses in the range from super Earth to Saturn masses. For the Seipel-Kozai-Lido scenario, they found that in its current configuration, its mechanism is not strong enough to produce high eccentricity values. While for the common envelope scenario, they found that the orbital energy available to eject the envelope was not enough. Just to confirm, are you still seeing my screen, right?
Yeah.
Yeah, thank you. Okay, so however, more detailed analysis made by O'Connor et al. 2020, Muñoz and Petrovic 2020, and also Stefan et al. 2020, showed that the Kozai-Lido scenario can indeed explain the close orbit of the planet. And in the case of the later, under this Seipel, in the case of Muñoz and Petrovic, they predicted a mass between 0.7 and 3 Jupiter masses for the planet candidate under this Seipel-Kozai-Lido scenario. In the same line, me and my collaborators showed that the type orbit of the planet can be also explained with a more detailed reconstruction of the common envelope phase. Well, it is also worth mentioning that more recent works like those carried out by Chamandi et al., the next talk, and Merlov et al. Support this common envelope scenario. So, to start, among all the scenarios presented to explain the short orbital period of the planet, the common envelope evolution scenario is less affected for what we call the age problem. So as I mentioned before, the estimated upper limit for the age of the entire system is 10 gigayears, and the estimated mass of the white dwarf is between 0.54 and 0.57 solar masses. So based on evolutionary tracks of single stars with masses up to 8 solar masses, we found that the time required to form a white dwarf in that mass range, plus the cooling time of the white dwarf derived by Van der Burg et al. Exceeds the upper limit of 10 gigayear. So this is a critical problem that all of the above scenarios have at some level. However, with the common envelope phase, the growth of the core is truncated, and therefore a more massive star with a shorter main sequence lifetime can be the progenitor of low mass white dwarf, which reduces the total age of the system. So this equation shows the energy formalism for the common envelope phase, in which a fraction given by this alpha parameter of the orbital energy released during the common envelope phase should be equal to the binding energy of the giant envelope in order to eject it. So all the solutions we found with the code developed by Monika Sorotovic meet this condition. So just very briefly, here G is the gravitational constant, and 1 is the mass of the giant star or the white dwarf progenitor. This term here is the mass of the giant envelope. The lambda parameter is adjusts the binding energy of the envelope according to the mass and evolutionary stage of the giant star. This term is the Roche-Low radius, or the equivalent volume radius of the Roche-Low at the onset of the common envelope phase. As I said before, alpha is the fraction of the orbital energy used to unbind the envelope of the giant star. MC is the mass of the giant's core at the onset of the common envelope, or in other words, the mass of the future white dwarf. M2 is the mass of the companion, in this case, the planet candidate. And these two terms are the orbital separations at the onset and immediately after the common envelope phase, respectively. So very briefly, this code works as follows. First, we calculated a grid a grid of stellar evolution tracks with masses up to 8 solar masses. And then, as the core mass of the giant star at the onset of common envelope evolution must have been equal to the white dwarf mass in the post-common envelope system, we first search in the grid for giant stars with a core mass equal to the measured white dwarf mass. And now, since we know the radius and the mass of each of the potential white dwarf progenitor stars, we can, for all of them, determine the orbital period or semi-major axis at the onset of common envelope evolution using the mass of the companion here in this term, the mass ratio, and the equation for the Roche low radius. So we replace this term here, and then we can obtain this parameter, this A parameter, and replace here. We also include in the lambda parameter the recombination energy, which may contribute to eject the envelope during its expansion. So finally, using the main sequence lifetime derived by the code and the white dwarf cooling tracks of Bedard et al. 2020, we can calculate the total age of the system. So the final results of our work are summarized in this figure that compare the total age of the system with the mass of the white dwarf. Here we have the age and the mass of the white dwarf. Well, according to Vanderburg et al., the white dwarf atmosphere is most likely a mixture of hydrogen and helium. So we use two limiting cases for the composition of the atmosphere: a pure helium atmosphere and a pure hydrogen atmosphere. Well, the red lines here represent the age of the thin disks, our upper limit for the age of the system, and here the age of the universe. The black line represents the best fit for the mass of the white dwarf, and the blue line is the age of the white dwarf assuming single stellar evolution. The black, gray, and dash gray areas represent solutions without considering recombination energy here, assuming the use of up to 10% of recombination energy here, and assuming the use of up to 100% of recombination energy, respectively, here. The same for this figure. So all solutions we found using up to 10% of recombination energy here eject the envelope during the thermally pulsating AGV, and the orbital separation at the common envelope onset is between 1.7 and more or less 2.3 AU, depending on the atmosphere model used. So you can see that since we found solutions, and these solutions fit better the discrepancy between the white dwarf mass and the age of the system compared to single stellar evolution models, common envelope evolution is at least as likely as the planet-planet scattering or the Seipel-Kosai-Lidov oscillation scenario. Well, a very important point, we choose this up to 10% of recombination energy value based on two post-common envelope binaries studied by Monika Sorotovich, which long orbital periods can be only explained by including up to 2% of recombination energy or another energy or another source of energy. And also an important point is that for these solutions, we assume a planet mass of 14 Jupiter masses, which is the upper limit derived by Vanderburg et al. We found that for planets with masses below 5 Jupiter masses, the common envelope scenario is not possible. Well, we also found that previous to the common envelope phase, Seipel-Kosai-Lidov oscillations could help the planet to migrate inward the separation required for common envelope evolution. In this figure, we can see that for the particular case of a white dwarf progenitor with a mass of about 1.7 solar masses orbited by a planet with 14 16 Jupiter masses at a initial semi-major axis of 5 AU, the eccentricity oscillations induced by the M-dwarf binary can migrate the planet to the required separation to experience Roche low overflow in the AGV or thermally pulsating AGV. So here, these are not the eccentricity oscillations, but are the Roche low radius oscillations produced by these changes, quasi-periodic changes in the eccentricity. And well, we also found that the planet would not be evaporated during the common envelope, and that the mass loss rate of the planet due to extreme UV radiation produced by the white dwarf immediately after the envelope ejection is negligible. So in this figure, we have the mass loss rate as function of the temperature of the white dwarf. Well, here you can see that, as I said before, that the mass loss rate is negligible. And here you have for reference the cooling age of two of these points. So obviously the mass loss rate decreases with the cooling age. And well, so as a conclusion, the main points I want you to take away are that common envelope evolution represents a reasonable scenario for the observed orbit of this planet candidate if recombination energy is taken into account, or more broadly, if another source of energy is taken into account. Also, common envelope evolution is less affected by the tension between the mass of the white dwarf and the age of the system. And also, in order to reach the separation required for common envelope evolution, the planet may have undergone some kind of migration prior or during the main sequence stage of the host star or the white dwarf progenitor. For example, this Seipel-Kozai-Lidov oscillation, this Kozai mechanism. Also, neither during nor after the common envelope evolution, the planet is significantly affected by evaporation. So the planet can survive all this common envelope phase. And also, a better estimate of the mass planet can provide more clues about the evolutionary history of this planet candidate. And about this point, the recent work of Alonso et al. 2021 estimated a lower limit for the mass of the planet candidate of 4.4 Jupiter masses at 1 sigma level, 2.4 at 2 sigma level, and 1.6 Jupiter masses at 3 sigma level. So, well, this estimation was based on the slope of the planet transmission spectrum, assuming a cloud-free atmosphere dominated by Rayleigh scattering. So, under this assumption, this lower limit for the mass of the planet candidate favors the common envelope scenario over the Seipel-Kozai-Lidov or the dynamical scattering scenario in a planetary system. And also, a very important point is that they conclude that the white dwarf is a DA white dwarf, which means that this scenario is more consistent for this system. This favors a bit more the common envelope scenario because the single stellar evolution model are have even more this conflict between the upper limit in the age of the system. So if the white dwarf is a DA type white dwarf, common envelope evolution is most likely than the single stellar evolution model. So, well, thank you very much. I think that's all from my side.
Thank you, Felipe. Do we have questions? So I see one raised hand from Sandino Estrada, then Ben Kaiser, and then there is a question in the chat. So maybe Sandino wants to ask the question.
Thank you. And good talk, Felipe. I would like to question you why the Lagos is equal to the radius 1 in your calculation. Why do you assume that?
Here, right?
Yeah.
Yeah, because here we assume, well, this assumption is made at the onset of the common envelope evolution. This means when the radius of the star is equal to the Rothschild radius.
So this is an assumption to start the common envelope evolution.
Yes.
Okay, thank you very much. Nice talk.
Thank you.
So next one is Ben Kaiser.
Hi, Felipe, thanks for the talk. It was great. I'm sorry if I missed this, but so based on this figure as well, you mentioned in the conclusions, there's no significant evaporation from the planet, but is there any significant accretion onto the planet from the envelope? And is that going to change the composition of the planet?
Well, we didn't explore that possibility, but yes, I mean, could be possible. As also could be possible that the planet itself was more massive at the beginning, and the evaporation indeed evaporates some amount of the mass, and we observe now a less massive planet. But yes, answering your question, we didn't explore the potential accretion of the envelope material to the planet. I don't know if I answered your question.
No, thank you. Yeah,
Then we have two questions in the chat. One is from Arturo, but there's no surname. So,
Arturo, this is me, Alberto. Alberto
Oh,
Rosa.
Alberto.
Yes,
Okay.
sorry. That's my son touching things.
Okay, you can ask the question yourself, and then Linda later.
Well, yes, I will just read it. So if the question is if you can measure the mass and the radius of the white dwarf from the transit of the planet, because if you can do that, then you can compare it to theoretical mass radius relations for helium core and carbon oxygen core white dwarfs. And if the data agrees with helium core white dwarf, then it should be common envelope evolution.
Well, I don't remember if from Vandenberg estimated the radius of the white dwarf. I remember that the planet obscure like half of the flux of the white dwarf.
Yes, they did estimate the radius. It was like 0.013 solar radii, I believe. Just a bit bigger than the Earth.
Thank you.
All right.
So what was the question? Sorry.
So if you have a mass and the radius directly measured from the transit without using any mass radius relation, then you can compare this data point, these data pairs with theoretical mass radius relations from carbon oxygen cores and helium core white dwarfs. If the mass and the radius, the observed values agree with helium core white dwarfs, then it has to be common envelope phase, because there is no other way to form a helium core white dwarf if it's not from this kind of evolution, right? So the idea is if this mass and radius can be measured, if they can be measured, and second, if they can be compared to these theoretical relations, because if by any chance the mass and radius observed relation agrees with a helium core theoretical relation, then it should be a common envelope evolution, I think.
Yes, well, yeah, I think you are right.
But I'm not sure if it's possible to measure this mass and the radius.
Well, the mass of the white dwarf is very uncertain. I mean, yeah, yes. In this work of Alonso et al., they derive the mass, also derive the mass of the white dwarf using archival photometry, but the errors in those measurements are also very uncertain. So they got at the same conclusion that the mass of the white dwarf is close to 0.52, but making some assumption in the errors, the best fit, or the best fit they got was about 0.6. So yes, definitively, a better estimation of the mass of the white dwarf could help to disentangle this problem.
Thank you.
Okay, I think I will read the last question from Linda Smith-Albright, and then we'll move on with the next talk. So Linda asked, she said, Zorotovich have looked at the large sample of post-common envelope binaries and found a common solution of the model using recombination energy. Is this value of 10% that is needed here consistent with the previous finding?
Well, we use this upper limit of 10%, just taking into account that it is a planet. It is not a M dwarf or a more massive companion compared to this planet candidate. So based on this, based on these two post-common envelope system, which can be all explained with the inclusion of recombination energy, of 2% of recombination energy, we assume an inclusion of 10% of recombination energy. This is one of the free parameters that is still very uncertain, and yeah, we just set this upper limit of 10% in our solution. I don't know if Monica can complement my answer, or
okay, maybe I don't know, maybe it's better you discuss this in the breakout session. I see
yes.
Matthias also raised his hand.